In this continuation of exercise 232, we're just trying to draw some resonance structures, all the resonance structures for some molecules that may have more than one resonance pattern. So here in C, we're given a molecule, and we're going to go through methodically, one by one, each of the 5 resonance patterns, see which one we have. Now the first thing you want to do is to draw in any lone pairs. That will help you to see resonance patterns. So we only have carbon here, and carbon only has a lone pair when it has a negative charge, which one of the carbons does. So that carbon is going to have a lone pair. So I'll draw that in right there. All right, so now we can go through the patterns. The first pattern, allylic lone pair, is that present? And it is. This lone pair is just one atom away from an atom in a double bond. So we have an allylic lone pair, and so we know we for sure have resonance. So we'll draw those brackets that warn people about the resonance and let them know this molecule never looks like any of these individual structures. It only ever looks like the average between them. And when you have an allylic lone pair, the pattern associated with that is that that lone pair goes to form a new pi bond toward the double bond, and the pi electrons in the double bond go to form a new lone pair away from the allylic lone pair. So you draw that special resonance arrow with this one line and the 2 heads that tells you to take the average of the 2 molecules on either side. And anywhere where you have the tail of a curved arrow, those are electrons that are going to be moving, so you erase those. And anywhere where you have the head of a curved arrow, that's a place where electrons are going to be arriving, so you draw those in. If the head of a curved arrow points at a bond, then you draw the incoming electrons as a bond. Anywhere where you have the tail of a curved arrow, those are electrons that are going to be moving away from there, and so you erase those. Anywhere where the head of a curved arrow is pointing, that's a place where electrons are going to be arriving. So you draw those in. If the head of a curved arrow is pointing at an atom, then you draw the moving electrons in as a lone pair. So that's our new resonance structure, and if you go through the original structure and draw in the hydrogens, so I'll do that very quickly here. You can pause the video and do it on your own, see if you get the same numbers, and if not, you might look back at previous videos where we've done this more slowly, going one by one. So those are your hydrogens, so that means on this new structure we have the same number of hydrogens. So this carbon has 2 hydrogens, this one has just 1, 2, and 3. Okay, so if you go through this, you can see that the formal charges have changed. This carbon here had a 0 charge, and the carbon at the far right, this one has with the lone pair, has the negative charge. So we went through the first pattern, an allylic lone pair, definitely had that there. How about an allylic positive charge? No, there's no positive charge in that structure. How about a lone pair next to a positive charge? No, there's no positive charge in the structure. How about a pi bond between atoms of differing electronegativity? No, we have a pi bond, but it's between 2 carbons, which have the same electronegativity. And we don't have a ring, so we couldn't have conjugated pi bonds in a ring. So that's the 5 patterns for that left structure. We want to go through all 5 for the right one. And so first, do we have an allylic lone pair? We do. This lone pair is just one atom away from an atom in a double bond. But if you go through the pattern for that, you'd see that that gives you the original molecule you start with. So that pattern is there, but we've already drawn the structure it would lead us to. So we don't have to do anything for that. We don't have an allylic positive charge because we don't have a positive charge in the molecule. We don't have a lone pair next to a positive charge because no positive charge in the molecule. We don't have a pi bond between atoms of differing electronegativity because although we have a pi bond, it's between two carbons, each of which has the same electronegativity, and we don't have a ring, so we couldn't possibly have conjugated pi bonds all the way around a ring. So these are the only two resonance structures for this molecule. And so the true molecule never looks like either one. The true molecule only ever looks like the average between the two, which would be something like this, with a slight negative charge in two places. And intermediate bonds in this area here. And also at the very end, you'd want to clean up those hydrogens. Because it's a bond line structure, you would just want those hydrogens to be implied. Okay. So now we can take our 5 patterns, we'll use them down here with our next structure. So, okay. For the structure, first step is to just draw the lone pairs in. It'll help you to see the resonance patterns a little more easily. None of the carbons have a negative charge, so they don't have lone pairs. But each of the oxygens only has 2 bonds, which means it only has 4 electrons around it. So you need to add 4 more electrons, in other words 2 lone pairs, on each of the oxygens to get them to have 8 electrons around them. So first, we'll go through this, see if we have any resonance patterns. Do we have an allylic lone pair? We do. This lone pair is not. Those lone pairs are not allylic. They're on an atom in a double bond. They're not one atom away. But these lone pairs are allylic because if you go one atom over, you're at an atom in a double bond. So we definitely have resonance here. We'll draw one of those. We'll draw those brackets to warn people. That all these structures we're drawing are not the real structure. The real structure is the average. So the pattern you get with an allylic lone pair is that the allylic lone pair goes to form a pi bond toward the double bond, and the pi electrons in the existing double bond go to form a new lone pair away from the allylic lone pair. And I'll draw the hydrogens in here just so it's easier for us to calculate formal charges later on. Okay. So you can take that molecule and here, anywhere we have the tail of a curved arrow, that's a place where electrons are moving away from, so you erase those. Anywhere we have the head of a curved arrow, it's a place where electrons are arriving, so you draw them in. If the head of a curved arrow is pointing at an atom, then you draw those arriving electrons as a lone pair. So anywhere where you have the tail of an arrow, those are electrons that are moving away from there, so you erase those. Anywhere where you have the head of a curved arrow, that's a place where electrons are arriving, so you draw them in. If the head of a curved arrow points at a bond, then you draw those incoming electrons as a bond. If you calculate the formal charges here, you'll see that this oxygen has a positive charge at the bottom, and the oxygen at the top has a negative charge. Okay, so we're still on this first molecule. We've only gone through the first pattern for it. Let's go through the rest. Is there an allylic positive charge in that first molecule? No, there's no positive charge in it. How about a lone pair next to a positive charge? No, no positive charge in it. How about a pi bond between atoms of different or differing electronegativity? We do have that. That's this bond right here. The double bond between the carbon and the oxygen. So we do have this pattern. So we'll draw another resonance structure for this. I'm going to draw that arrow there. And what happens in this pattern is the pi electrons go onto the more electronegative atom. So we'll copy this. Anywhere where you have the tail of an arrow, those electrons are moving away from there, so you erase them. Anywhere we have the head of an arrow, those electrons are arriving at an atom, so you draw those in. And if you calculate the formal charges, you'll see that that oxygen has a negative charge, and the carbon next to it has a positive charge. Okay, we're still on this first one. We've gone through the first 4 patterns. Let's just go through that last one. Do we have a conjugated pi bonds in a ring? No, we don't have a ring, so we definitely don't have that. Okay, let's look at the next resonance structure and go through the 5 patterns for that one. This resonance structure is this one right here. Is there an allylic lone pair there? There is. They're the lone pairs in the oxygen at the top. The other oxygen, those lone pairs are not allylic. Those are on an atom in a double bond, but at the top, those electrons are allylic because if you go just one atom away, you're at an atom in a double bond. The thing is, though, if you do the pattern for that, then you end up with the same molecule you started with. So that pattern is there. You do have an allylic lone pair in that structure. So we do have that, but we've already drawn the result of that pattern, so we don't have to draw anything for it. How about an allylic positive charge? Do we have that? No. We do have a positive charge in this molecule, but it's not one atom away from an atom in a double bond. It's on an atom in a double bond. So we don't have that. How about a lone pair next to a positive charge? No. We have a lone pair on an atom with a positive charge, but not a lone pair on the atom next to an atom with a positive charge. How about a pi bond between atoms of differing electronegativity? We do have that. This bond right here, that double bond, is between a carbon and an oxygen. So the first bond there is a sigma bond, but the second one is a pi, and so we do have a pi bond between atoms of differing electronegativity. So we'll have that pattern, that curved arrow pattern there. So I'll draw that special resonance arrow that tells you to take the average. I'll copy my molecule, and wherever you have the tail of a curved arrow, those are electrons that will be moving away from there, so you erase those. Wherever you have the head of a curved arrow, that's a place where electrons are arriving, so you'll draw them in. If the head of a curved arrow is pointing at an atom, then you draw the electrons as a lone pair. So we'll draw that lone pair there. And if you go through and look at the formal charges, you'll see that that oxygen no longer has a positive formal charge, but the carbon here does. And now that you've drawn that, you can see that that is actually the same as this other structure that we drew. So we actually don't have to include that one. I mean, I should say it's already included. So we've already taken that into account. So we have this one, but we've already drawn it. And we definitely don't have conjugated pi bonds in a ring here. We don't even have a ring. Okay, so those are 2 structures. Now we want to go through all 5 patterns with this last structure that we have. First, is there an allylic lone pair there? There's not. There's no double bond in this molecule, so you can't have a lone pair that's one atom away from a double bond. How about an allylic positive charge? No, we don't have a double bond, so nothing can be allylic. How about a lone pair adjacent to a positive charge? Yeah, we have that in 2 places, here and here. Both of those are right next to a carbon with a positive charge. But notice if you go through the pattern for that, bring these electrons down, in that case you'd end up with your original molecule. If you bring these electrons over, in that case you end up with this molecule. So we do have that pattern, but we've already drawn the structures you get from it. So we wouldn't draw them again. How about the 4th pattern? Do we have a pi bond between atoms of different electronegativity? No, there's no double bond there, so there are no pi bonds there. And how about a conjugated pi bonds in a ring? No, we don't have a ring. So these are the 3 resonance structures for this molecule. And that just means you have 3 resonance structures, so there's a lot of resonance there. That means that the molecule is really stable and also rigid. And the true structure never looks like any individual of these structures, it's the average of them all. Let's just do this one before we go on. We finish it. We finish this video and leave the rest for another one, another video. So here, first just draw the lone pairs in. None of the carbons have lone pairs because none of the carbons have a negative charge. The oxygen needs 2 lone pairs in order to get 8 electrons around it. So first, does that molecule have an allylic lone pair? No, it doesn't have a double bond, so nothing is allylic. Have it an allylic positive charge? No, you don't have a double bond there, so you can't have a positive charge that's 1 atom away from the double bond, an atom in the double bond. How about a lone pair next to a positive charge? And that we do have. So we have resonance, you draw those warning brackets. We have our molecule here. And the pattern is that the lone pair goes toward the positive charge. So we use those special resonance arrows that tell you to average the molecules. And I'll just draw in all the hydrogens. You can always check if you have the right number by using that formal charge equation. So those are all the hydrogens there. So to draw the other resonance structure of this, we'll just take this, copy it, and anywhere where you have the tail of a curved arrow, those are electrons that are moving away from there, so you erase them. Anywhere where you have the head of a curved arrow, that's a place where electrons are arriving, so you draw them in. If the head of the curved arrow is pointing at a bond, then you draw those incoming electrons as a bond. So that goes there. Now, if you calculate the formal charges here, you'll see that the oxygen has a positive charge. And just to draw this a little better, that oxygen, the double bond is going to that oxygen. So. And you'll also see that this other carbon has no charge. Okay, so we did have that third pattern, lone pair adjacent to a positive charge. Still looking at this first structure, was there a pi bond between atoms of differing electronegativity? No, we didn't have a pi bond, so we couldn't have that. And in that first structure, there's no ring, so you couldn't have alternating single and double bonds all the way around a ring. Going through the 5 patterns for the second structure, this one, is there an allylic lone pair? No. There's a lone pair, but it's on an atom in a double bond. It's not 1 atom away. Is there an allylic positive charge? No. There is a positive charge, but it's on an atom in a double bond. It's not 1 atom away, so it's not allylic. Is there a lone pair adjacent to a positive charge? Nope. There's a lone pair on the same atom as a positive charge, but not a lone pair on the atom next door to a positive charge. So we don't have that one. How about a pi bond between atoms of differing electronegativity? We do have that between this oxygen and the carbon. The second bond there is the pi bond. The pattern for that, though, is that the pi electrons go to the more electronegative atom, and notice that would bring us back to our original structure, so we don't have to draw anything for that. We do have the pattern, but we've already drawn the structure we'd get from it. And then last but not least, we don't have conjugated pi bonds in a ring because we don't even have a ring. So those are the 2 resonance structures. The fact that they have resonance structures means that the charge is spread out, and so that stabilizes the molecule. Also, the bonds tend to be somewhere in between, something bigger than single, so they have some pi bond character, which makes them unable to rotate, so the molecule is more rigid. And so those are the resonance structures for E. So we'll continue with F and G and H and I and J in another video because I want to avoid making the videos too long.